Chapter 1, Section 3. We begin this year in Algebra 1 talking about number sets. We're going to go through all the different number sets that exist in Algebra 1 that we're going to see. There are more numbers out there, but really there aren't that many that we're going to be looking at even through the high school years. But this year, these are the most common numbers that you're going to be seeing, the number sets you're going to be seeing. These are basically where all the numbers that exist in Algebra 1 live. Imagine all the easiest numbers live in a box. You take the numbers 0, 1, 2, 3, 4, 5, 6, 7, all the way to 100, to 1,000, to 1,000,000, to 1,000,000,000, and beyond. And all those numbers you put in this fence, in this box. That would be the whole number set. So those numbers are 1, 2, 3, all the way to infinity. Put those in the box, there's one set. All those numbers, 1 through infinity, belong to that set. Now there's another set that includes all the whole numbers. Okay, it basically envelops them, and it adds on even more numbers out here in this area. This number set is called the integer number set. The integer number set includes all the whole numbers. 1 is an integer also, 2 is an integer, 3 is an integer, so all those numbers are part of the integer set. This box is inside this other box, but then we add on some more. We add on -1, -2, -3, all the way to negative infinity. All those numbers are integers. 1's an integer, 2's an integer, -1's an integer, -2's an integer, so on and so forth. Outside of that, we have a larger box. It encloses and includes all the integers, which includes all the whole numbers. This is an even bigger set of numbers, because what we're doing is we're looking at the rational number set, which are all the numbers in between our integers and our whole numbers. In between between 0 and -1 is -1/2. In between 0 and 1 is +1/2. Fractions and decimals live here. Notice I put this decimal right here. I'm going to come back to this later, but 3.5555, it would be the same as 3.5 repeating. That's a rational number. So that pretty much rounds out most of the numbers we're going to be looking at, but there are some others that are really ugly that nobody likes to deal with too much, and we call those irrational numbers. A number cannot be rational and irrational at the same time. This box is all on its own. But numbers like square root of 2, and this is pi, are irrational numbers. One way you can easily tell if something is irrational is if you type it in a calculator and it keeps going on forever. Now, calculators only go out to about 8 or 9 digits, so sometimes that's tricky. But the rule is it's rational if you can write it as a fraction. All these numbers can be written as a fraction. For example, this would be -12 and 2/10. This would be 3 and 5/9. Anything that has a repeating number, a single repeating number, is ninths. 0.1111 is 1/9, 0.2222 is 2/9, and so on and so forth. So repeating decimals like this can be written as fractions, which is why they're rational. Most roots are irrational, but there are a few that aren't. For example, square root of 3. That's irrational. It belongs here. But square root of 4 is rational because you can simplify it. When you simplify it, it becomes a whole number, and that belongs over here. So before you choose what place it's in, you have to be able to simplify that number. Okay, so we're going to try to classify numbers based on which set they belong to. The first one is -17/31. Now imagine that we have that box back. Which set would be -17/31? It wouldn't be the whole numbers because that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wouldn't be -1, 2, 3, 4, 5, 6, 7, 8, 9, 10 either. It's actually going to be rational. Rational numbers can be negative also. So we would write rational. next number, 23, that would belong in the smallest box in the whole numbers box. It's one of those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a whole number. Now, the question is that the only box that belongs to? And the answer is no. If we go back to here, this box is actually in this box. So whatever is in here is also an integer. And whatever is in here is also a rational number. So technically, it's whole, it's integer, and it's rational. 0 is a whole number. And so since it's in the smallest box, it's also in the integer box. And it's rational. Finally, 4.581, that would belong in outer ring. It's not an integer, it's not whole, it's just rational. So, next step, you're going to try it. You're going to name the set or sets of numbers to which negative 4.67 belongs. Is it A, whole, B, rational, C, integer, or D, irrational? And there's your set. Picture again. Whole, integer, rational, or irrational. The answer is B. And for practice, you would want to do page 20, 1 through 13 all for more of those problems. Example 2 is about reasonable numbers. We're going to look at situations and we're going to ask ourselves, what's the best set that defines this example or this situation? The first situation is, what set of numbers would we use to describe the number of students who will go on a class trip? Possible example of numbers of students who would go on a class trip is, say, 25. Or we could have a smaller group of 5. Or we could have 13. What we can't have is negative 15 students. Or the square root of 27 students. Or 3.5 students. Those are not possible numbers. So the only number set that would work in this case is whole numbers. The height of a door frame is another thing we could try to talk about what number sets would work. Now some door frames would be 10 feet or 8 feet or something whole. Door frames can't be negative numbers, but there are positive rational numbers. There's doors out there that are 8.5 feet more than likely, or 12 1/4 feet. 12 feet 1/4, 12 feet 3 inches. And those would be possible heights of door frames. And all of these numbers could best be defined as rational numbers. So the answer to this one would be rational. Okay, so you try this one. Try to figure out which set of numbers, and we're just talking about a single one, the best set is most reasonable for the cost of a scooter. Is it A, irrational, B, whole, C, integer, or D, rational? Go ahead and pause that now and think about it, and then unpause when you're ready. Okay, the answer is D, rational. For more practice, you would want to do page 20, 14 through 18 all. Example 3. Is the statement true or false? If false, give a counterexample of why. Now, we need to first define what a counterexample is. This word right here. If I give a statement, a counterexample proves that statement isn't true. Can you give an example? Let's say I say that yesterday there were clouds in the sky and therefore it rained. Or I should say, there were clouds in the sky, and therefore it was going to rain, no matter what. So the statement is, if there are clouds, it will rain. You could say, as a counterexample, yesterday there were clouds in the sky and it did not rain. So that would be a counterexample, a specific example that proves my statement false. So for the first statement, all whole numbers are rational numbers. So you think about your whole numbers, you think about your integers, you think about your rational numbers. All these numbers in here are also inside the bigger box. So there is not a whole number that exists that isn't in this box. Because of that, we can say this is true. Every whole number is also an integer. The second one is the square of a number is always greater than the number. If I give you an example, let's say if I'm thinking of a number 3, if I square that number, the square of that number is always greater than a number. At first, you could think of lots of examples where this is true. But there is an example, a counterexample, that proves this is false. The number 1, if it's squared, is not greater than its number. 1 is not greater than 1. And when we square 1, we get 1. So this is a counterexample. We would say false because of this example right here. So you try. True or false? All whole numbers are integers. A, true, or B, false. Go ahead and pause it until you're ready, and I'll get the answer. Okay, moving on. The answer was A, true. For more practice with these counterexample problems, it's page 2019 through 23 all. Example 4, ordering fractions. We're going to write -3/8, -1/2, -5/12 in order from least to greatest. There are two ways to do this. The first is using the number line, chopping up the space between -1 and 0. Basically, all of these numbers live in between -1 and 0 on the number line, somewhere on here, but we don't know where yet. So what we're going to do is we're going to chop up the space into these portions and see if we can figure out which one's greater and which one's least. We have to be kind of accurate doing this method. So I'm going to get out of PowerPoint, go to my drawing board, -3/8, -5, -12, and -1/2. Sorry, something's going on with my writing utensil. I have to just go with pink today. Okay, so those are our three numbers. Here's our number line. Ugh. Okay, good as it's going to get. Here's -1, and here's 0. Now, we're going to make this many spaces, and this many spaces, or this many dashes from 0 to -1. Starting at 0, if I want to have 2 dashes, this is my second, so halfway is my first. That means -1/2 is one jump out of 2 on the way to -1. That's the easy one, -1/2. The next one is negative 3/8. We need 8 equal dashes. So the best way to do this is think about, okay, between 0 and, imagine this is 8. We go all the way to 8 here, starting at 0. What's halfway there? And in this case, 4 would be. So we need 4 dashes here, 1, 2, 3, 4 here, and 1, 2, 3, 4 here. Halfway between 4 and 8 is dash 6. So this is 6. This means this is 7. This is 8. And between 4 and 6 is 5. And halfway between 0 and 4 is 2. Halfway between 2 and 4 is 3. Halfway between 0 and 2 is 1. So there's our 8 dashes. That's a good way of making pretty even. The next one's a little bit more difficult. Well, before we get to that, negative 3/8 is 1, 2, 3 jumps along that way out of 4, 5, 6, 7, 8. So negative 3/8 is right here. Okay, last but not least, negative 5/12 is the next number we need to figure out. Now, halfway between 0 and this is going to be 12, we need to figure out the halfway point. Well, half of 12 is 6, so this is 6 this time. I'm actually going to write 6 so this we can keep track of it a little easier. So this is 6. Now, halfway between 0 and 6 is 3. Halfway between 6 and 12 is 9. Now, we need to know where 5/12 is. So this is negative 3, this is negative 6, negative 9, negative 12. This is 0. To go along 5, between 3 and 6, there's actually 4 and 5. So we need to kind of space this out somewhat evenly. Something like that. So 4 would be right here, 5 would be right here. And that is where negative 5/12 would be. So we can see clearly, oh, and least is over here, always on the number line, least is farthest left. So even if it's a bigger negative, it's less in our minds, because owing money is way less than having money. If you owe more, you have less. So there's least and there's greatest. So from least to greatest, we would have negative 1/2, negative 5/12, and then negative 3/8. The other way is to convert them to decimals using a calculator. Going back and clearing this all off, we can open up a calculator and we can type in negative 3 divided by 8, and that's going to be 0.375. Negative 1/2 is going to be negative 0.5, and negative 5/12 is going to be 0.416 repeating negative. So the question is, how do I know which one's bigger? A lot of students, when they're learning about place value or having a difficult time with place value, will look at this and go, okay, 416 is greater than 5, so I know that 465 is going to be farthest right, because 465 is the most out of all three. That's not a right way of looking at it. What you need to think about is having all the place values that are the same. So there's 3 place values in these two numbers. This one only has 1, so add zeros. Now think about it as 375, 500, and 416. Now if these were normal positive numbers, we would go the least is 375, the next is 416, and the next is 500. But they're negative, so you got to think about it backwards. The least is actually the greatest negative. So negative 0.5 is the greatest negative, which means it's the least. And then 0.416 negative is the middle number, and negative 0.375 is actually the greatest because it's the smallest least. We need to write these as the our original numbers because they were given us to us as fractions. So we need to rewrite this as negative 1/2. We need to rewrite this one as negative 5/12, and we need to rewrite this as negative 3/8. So that's both ways you can do this. You can either use a number line to chop them up evenly or convert them to decimals. So you try this one. You're going to write 1/12, negative 2/3, and negative 5/8 in order from least to greatest. Go ahead and pause now. Spend a few minutes to work this one out. Either use the number line or use the decimals. Okay, the answer to the previous one was C, which is negative 2/3 is the least, negative 5/8 is next, and 1/12 is the greatest. So you want to do page 21, 29 through 33 for practice on those. Example 5, finding absolute value. The absolute value of a number is the number's distance from 0. Basically, on a number line, the number 0 is in the middle, however far away your number is, so 12, positive 12, the absolute value of that is the distance from 0 to 12, which is 12 units. So the absolute value of 12 is 12. The absolute value of negative 2/3, here's negative 1. Negative 2/3 is about right here. So the absolute value of negative 2/3 is 2/3 of a jump over. The absolute value is 0. The distance from 0 to 0 is 0. So you try. Find the absolute value of 5/7. Is A 5/7, B negative 5/7, C 7/5, or D negative 7/5? Pause it and figure it out. The answer was A, 5/7. And for practice, you'll want to do page 21, 34 through 41. Alright, that's it. Good luck.